Hello and welcome to lecture 32 of our Essentials of Semiconductor Device Physics course. In this lecture, we begin a series of 3 videos leading to the relationship between current and voltage in a p-n junction. So last time we discussed the main features of a p-n junction out of equilibrium. We discussed the forward bias configuration, the reverse bias, and this time we're going to begin a mathematical analysis of p-n junctions out of equilibrium. And this analysis will lead to the famous Shockley equation, which describes the relationship between current and voltage in a p-n junction. And to do that, we're going to assume that we are in a forward bias condition, but the equation we're going to derive is valid for both forward and reverse bias, so we don't lose generality with this assumption. Let's begin by taking a look at some features of the current in a p-n junction. So let's suppose the p-n junction is in forward bias and there's a current I flowing through the junction. So this current I is actually the total current. The total current is composed of two contributions, the current of electrons and the current of holes. So I'm showing the current of electrons in red and the current of holes in green. And here we have a sketch of the current as a function of space in the p-n junction. And you can notice that inside the depletion region, I drew the current of holes as higher than the current of electrons. That does not need to be the case. The current of electrons could be higher or they could be the same. I just drew them differently because I think it's easier to see. Now, one important feature to notice is that the total current is constant across the p-n junction. And that makes sense because this is the current flowing the circuit. So if a current I enters the p-n junction, the same current I has to leave the p-n junction. So it must be constant across the p-n junction. But the current of electrons and of holes, they are not constant by themselves. Only their sum is constant. For example, you can notice that in the n-doped region and away from the depletion region, like in here, for example, the total current is given by only the current of electrons. The current of holes goes to zero away from the depletion region due to recombination. So the holes are diffusing from P to N, and then they recombine when they enter the n-doped region until their contribution vanishes. And the same feature happens on the other side. So the contribution of current of electrons away from the depletion region in the p-doped side also goes to zero due to recombination. And in this lecture, we're going to discuss the main features of these currents to gain insights on their behavior and to choose a strategy to calculate the total current. But as usual, instead of discussing the current itself, we're going to discuss the current density because that's more convenient. So we're going to be discussing the current density, the total current density, the current density of electrons, the current density of holes. And then when we find a relationship between the current density and the voltage, we can just multiply it by the cross-sectional area to get the total current, the current itself. Now recall from previous lectures that this black arrow represents the internal electric field and the red arrow represents the external electric field of the p-n junction in forward bias. And we have been assuming that the external electric field is also entirely confined within the depletion region. We've been assuming that there is no contribution of the external field, neither in the p nor in the n-doped side. So in this lecture, we need to justify a bit better why the external electric field is confined within the depletion region. And to do that, we're going to use this relationship for the drift current that we discussed in lecture 27. So recall that the drift current is proportional to the electric field. The constant of proportion is the conductivity, and the conductivity depends on the concentration of charge carriers. So the conductivity of electrons depends on the concentration of electrons, and the conductivity of holes depends on the concentration of holes. So the first feature to notice is that the conductivity of electrons in the n side is very high. And that makes sense because in the n-doped region, the n side, the concentration of free electrons is very high. So the conductivity of free electrons is also very high. And at the same time, the concentration of free electrons in the p-doped region is very low. So that means that this term is low in the p side, which entails that the conductivity of electrons in the p side is very low. So this term is high in the n side and low in the p side. Now, of course, we can make a similar analysis for the conductivity of holes, and we're going to reach a similar conclusion, but now it's the other way around. So the conductivity of holes in the n side is low because the concentration of holes in the n side is low, and the conductivity in the p side is high because the concentration of holes in the p side is high. Now let's take a look at the drift current of electrons in the n-doped region, in the n side. So this drift current depends on the conductivity of electrons in the n side. And we've just seen that this conductivity is very high because the concentration of electrons is high in this region. So the reason why the electric field is sufficiently low in the n-doped region so that we can dismiss it and consider it as being concentrated only in the depletion region is precisely because this conductivity is very high. It's the same reason why we dismiss the contribution of the electric field in a metallic wire when we are doing circuit analysis. It's because the conductivity of the wire is very high. In other words, we are stating that if this term goes to infinity, then the electric field must go to zero if the current is finite. Now, this is an extreme condition. What happens in reality is that this term is sufficiently high so that this term is sufficiently low to allow us to dismiss its contribution in the n-doped region. Now we can follow a similar line of reasoning for the p side, but considering the drift current of holes. So in this case we have the conductivity of holes is very high, which means that the electric field is sufficiently low so that we can dismiss it. So notice that the statement that the electric field outside the depletion region is sufficiently low so that we can dismiss it is a practical statement. It depends on how we doped it. If we dope it in such a way that this term or this term is not sufficiently high, then we cannot conclude that the electric field can be dismissed in the N and P doped region. But as it turns out, it is usually the case in practice that the doping is sufficiently high to allow us to make this approximation that the external electric field is entirely confined within the depletion region, that it can be dismissed, we can dismiss its contribution in the N and P doped regions. Okay, so now let's take a look at the current of electrons and holes on both sides of the p-n junction. Let's begin by taking a look at the current in the N side. So as usual, we have two contributions for each current. We have the drift current of electrons and the diffusion current of electrons, and we have the drift current of holes and the diffusion current of holes. And we know from lecture 27 that the drift current is proportional to the electric field and the diffusion current is proportional to the gradient of the concentration of charge carriers, electrons for the N current and holes for the P current. Now let's examine this product here. We already know that the electric field is low. But we also know that the conductivity of electrons in the N side is very high. So here we have a product of a large number and a small number. So there's not much you can say about this product. But what about this one? So here we have the conductivity of holes in the N side. And we know that this conductivity is low. So here we have the product of a small number and another small number. So that means that we can dismiss this contribution. In other words, we concluded that in the N side, in the N-doped region, the current of electrons has two contributions, drift current and diffusion current. But the current of holes has only one contribution, the diffusion current. We can dismiss the contribution of the drift current of holes in the N-doped region because the concentration of holes is very low, which means that the conductivity of holes in the N side is low, and since the electric field is already very low, we can dismiss the drift current. So we reached an important conclusion. This current here, represented in green, is a current of diffusion. It's only diffusion current, whereas this current here is a combination of drift and diffusion current. So the current due to holes in the N side is usually called a current of minority carriers, because holes in the N side, they are a minority. Their concentration is low. So we've concluded that the current of minority carriers, holes in the N side, is due only to diffusion. It's only a diffusion current. And of course, we can reach a similar conclusion analyzing the P side. So in this case, we have that the conductivity of holes is very high. So the conductivity of holes in the P side is high. So here we have the product of a large number and a small number. So there's not much you can say about this product. But here we have the product of a small number, because the conductivity of electrons in the P side is low, and another small number, which means that this product will be a very small number. So we can dismiss this product. Okay, so we've concluded that the current of electrons in the P side, the p-doped region, is only by diffusion. It's a current of diffusion. So in this case, the electrons are the minority carriers. So we've concluded again that the current of minority carriers is a diffusion current. So on both sides, the current of minority carriers is a diffusion current. And that is a very important conclusion, because recall that our job is to calculate the total current. So we could calculate this current taking the current at any point across the p-n junctions. For example, we could pick this point here, calculate the current of holes and then of electrons at the same point and add them up, or at this point or at this point. We can pick any point in principle. But we want to avoid calculating the current of majority carriers, so electrons on the N side and holes on the P side, because this current involves a drift current, and we don't even know what is the electric field. We only know that we can dismiss it for the minority carriers, but we cannot dismiss it for the majority carriers because the conductivity is high. So we cannot dismiss this product, and we cannot dismiss this product. So we want to avoid having to calculate this current and having to calculate this current. So we could, in principle, calculate the current at this point here and the current at this point here, and take advantage of the fact that the current within the depletion region does not change significantly. So if we take advantage of this, the constancy of the current within the depletion region, by calculating this current here at the edge of the depletion region, we are essentially calculating the current at any point within the depletion region, including this point. So we could then add with this current here, which is also a current of minority carriers because it's at the edge of the depletion region. And with this strategy, we will avoid having to calculate this current and this current. In other words, we're going to calculate the current inside the depletion region by calculating the current at this point and the current at this point. So our strategy then is to calculate the total current by evaluating the current due to electrons at the edge of the depletion region and the p side, so at this point. So this is why we're writing here the current, which is a function of space, but evaluated at a specific point, the edge of the depletion region with the p side, and the current of holes evaluated at the edge of the depletion region and the n side. And I emphasize once again that we are only allowed to calculate the total current by taking the two contributions at different points because the current within the depletion region is almost constant. We could not, for example, have taken one current here and another current here. That would not give the total current. But we can take it here and here because they are basically constant within the depletion region. Okay, so now that we established a strategy to calculate the total current by using only the diffusion current of minority carriers. And in the next lecture, we're going to follow this strategy to find expressions for the current of electrons and holes, in other words, for the total current, in terms of the concentration of excess charge. And we're going to discuss what that means in the next lecture.